we were talking about how I got interested in tin oxide electrodes. So it was in the early 60s and about 64 when I was doing work on a number of different electrodes which I was hoping would be more inert than the noble metals. Because one of the problems with electrodes like platinum and gold is that if you go strongly anodic, you form an oxide layer on the electrode, and then this is reduced back when you go cathodic. So this gives you an inevitable blank that happens if you're trying to do coulometric work, for example. And the blank is by no means negligible if you're doing trace analysis. So we're searching for something better. And I had heard about infrared reflecting glass, which is electronically conductive. And this was commercially available, so we started with that. And one of the immediate problems we found with that was that if we ever went cathodic enough with it to generate hydrogen on it, why, we lost the whole layer of tin oxide. It was reduced to, and we later proved that it was reduced to actually metallic tin electrochemically. But it disappeared. And so then we gradually were trying to make our own. But one thing I was going to talk to you about was our efforts to make bulk SNO2. And we wanted to start with a highly pure form. Now, as you know, SNO2 is a weighing form in gravimetric analysis. It goes way back to Berzelius, for example. And there's some curious phenomena if you read the analytical literature. You find, for example, that if you take a precipitated tin oxide and you ignite this to remove the water, that there's always a color change. Now, the usual thing I was taught, for instance, as a sophomore, was that, well, collected this on filter paper or something, you got carbon reduction of the stuff, and so then you got to reoxidize this. And in fact, the procedure always calls for oxidation under a blast lamp or something like this and it becomes white. And so the traditional lore was that you would get some carbon there, which you had to burn out, and then you would come out with the right stuff. And it's interesting that it was very close to being stoichiometric when you did this. You didn't have any finagle factor in the gravimetric factor. Well, as it turned out, I had a guy from Yugoslavia who was kind of a weird fellow, but he was an energetic type, and he decided he would start with stannic chloride and precipitate by adding ammonia to this, and then get the stuff. Well, it's a highly developed surface, and you just shudder at the impurities that you might be carrying down. So he tried a number of tricks, including dialysis to remove the electrolyte from it before he ignited it down. And he always found that he got some colored material all right without using any paper or whatever. We take a glass filter and you still get a dark. And indeed, it did become white eventually. But the interesting thing was that in the process of becoming white, it gained weight. So that what evidently was happening was that it lost weight under mild ignition and then gained it back. And one explanation of this would be that you actually had a lower valent tin, but not due to reduction, but due to loss of oxygen as such. In other words, you'd have a defect lattice type of stannic oxide, which then would reoxidize to give a hydrated stannic oxide and then igniting that. And when we had that analyzed, we used spark source mass spectrometry, so it was a very sensitive analysis. We always found chloride. And we could only presume that this chloride in such a case was obtained from bits of ammonium chloride fumes, for instance, that you might find in the wood or in the atmosphere. But I was struck by the fact that no matter how carefully you'd made this stuff, you'd have something like 0.1% or so of chloride in it, and that's appalling, you know, when you start thinking of atomic weight accuracy or something like that. So anyway, then, but we found that this color was real, and indeed seemed to be color centers in it. We had big arguments about what it was and so on, and that we could also get colored materials if we took the thin film stuff and partially reduced it electrochemically. It turned dark. But I had a postdoc by the name of Ted Bednarski, who was one of these practical type guys, and he wasn't going to fiddle around talking about color centers and so on. He says, let's analyze the beast. And so he succeeded in actually extracting metallic tin from this product by means of mercury, and then showing by anodic stripping that the mercury contained a bit of tin. Well, that was a pretty solid proof, you see. We pull the metal out of it. So then we investigated further electrochemically and concluded that indeed that's what happens under very strong reduction, that hydrogen simply cannot be generated on that surface without eventually losing the structure of the stuff. But anything short of that, it's an extremely stable, it's remarkably stable material. You could go to strong anodic potentials without losing it and so on. So that started us then on a program of using this as a very inert anode. And we've done tricks like, for instance, generating divalent silver in aqueous solution on it. And it's definitely better than platinum or gold for this sort of purpose, than using this divalent silver as an oxidant for coulometric titration or something like that. So the stuff is really a rather remarkable material. Well then, in the process of doing this, one of the things that we were using analytically was lead. And what we wanted to do was simply to plate lead, as in the classical gravimetric analysis, plate it as lead dioxide, and then coulometrically reduce it back to lead in solution. And this would be an extremely sensitive method of analysis. The only catch was that we had an entirely different problem we hadn't anticipated, and that was nucleation. That is, here's one solid precipitating on another one. And that led to a whole PhD thesis just studying the nucleation and the growth of these lead dioxide particles. It turned out that that had been done beautifully before by Fleischmann in England, and that our results could be neatly dovetailed into his, only he did it on platinum, and ours was much superior because we had far smaller blanks and so on, so we got cleaner results, but the results were very much the same. In other words, that the lead dioxide had to nucleate on this foreign surface, and then these nuclei would grow relatively rapidly once they'd grown. And in fact, that they would grow without any preference as to direction. So you get hemispheres, if you please. And we could demonstrate this by electron microscopy, actually see that we had round particles, and furthermore, that these particles are different in size, showing that the nucleation was happening all the way along. This is at high overpotential. Mm-hmm. So that you would be forming new nuclei, but once you form them, they would grow. And this would then eventually give rise to a complete coverage of the electrode by lead dioxide. But you can imagine a sort of bunch of little hillocks starting at points and then growing together to form a kind of a bumpy surface. And then the remarkable thing is that if you strip this off, the crystalline material comes off right at the reversible potential. You get a huge peak if you plot current against potential, right at the reversible potential. But you don't get it all. There's always a small residual amount that is left, and this takes about up to 7/10 of a volt of overpotential cathodically to remove it. And so the conclusion out of all this was that, yes, you can remove the crystalline material, but when you get to that last monolayer on the surface, that is much more difficult to reduce. And so it no longer comes off at the reversible potential. And I've always wanted to use that as a possible trick to nucleating other things. You see, suppose you plate it completely with lead dioxide, and then remove all but the first monolayer. Shouldn't that be a good nucleus for something like manganese dioxide? I think it's, I've never gotten anyone to test this yet. You always have these problems. You got to bludgeon someone into doing it. I guess nobody else is that much interested. So I told you about my new Japanese worker. I tried this out on him. It terrified him. He's just so scared of something like that he didn't want to touch it with the proverbial 10-foot pole. So I backed off. I mean, I don't really care if he does it that way, but however we could make a thin layer of MnO2, that would be fine with me. But see, we had done some work on using tin oxide as a surface for this, but later we found that you could simply take titanium. That's what they use commercially, after all, in making commercial MnO2. So I don't see any reason now that one couldn't simply use titanium anodes and plate these layers I was telling you about. That's what we're trying to do.
When did you become interested in electrodes and electrode chemistry?
Oh my goodness. My graduate work with I.M. Kolthoff back in the mid-1930s. There's a little story to that too, because up until that time, see, Kolthoff had worked a lot on precipitates and had done huge studies, but about 1934, in fact it was 1933, when Harovsky came over and gave a series of talks, and he visited Minnesota. Now Kolthoff had known Harovsky before, back in his trips to Europe that he made every summer, but he never got interested in electrochemistry especially. But when Harovsky came over, there was a student by the name of Jim Lingane who was just ready to undertake a thesis problem, I think in '34. And he convinced Kolthoff that this would make a neat thesis project for him. So he started. Well, he was the first of a whole group then of electrochemically oriented students. And I was right on target. I was an undergraduate there, and I had been sneaking in on some of the seminars and so on, so I knew what was going on. And I was so completely frustrated by certain kinds of lab work, like, for example, organic synthesis. I was terrible at it. My yields would be among the lowest in the class and so on. So there are some kinds of things that just didn't appeal to me, like handling these precipitates. But one day I went into Lingane's office, or his lab, and he was perched on a stool by a lab bench, working with a homemade manual plerographic apparatus. And this, he had a corncob pipe in his mouth, and he had a bound notebook open. He was writing in ink, and it seemed so neat. It was so nice. He would change the voltage by 1/10 of a volt or whatever, and then he would watch the galvanometer go as the drops of mercury came, and he got a balance, and he would just write that down in ink in a nice neat row column. And I watched him for a while doing this, and I thought, boy, there's a way to do research, you see. It's peaceful and clean and all that. And then later he showed me the plot that he got, and he plotted up the curve, a beautiful S-shaped curve, you know, fine. But then somehow I got talked into doing solid electrodes, not the dropping mercury electrode. That was another ball of wax completely. Not so neat and so clean, because you would have all kinds of horrendous problems, at least the way I did them. Because in those days we didn't have all kinds of fancy recording equipment that you could record things in a rapid time scale. And so I undertook to study diffusion processes as measured electrochemically. And if you set it up just right, for instance, if you have a linear diffusion column going either up or down in such a way that the density gradients are in the right order, well, then you can sustain this column for minutes and follow the law of linear diffusion. Well, that was all in the literature. In fact, diffusion theory has been known way back in the 19th century. But there hadn't been any really applications of this, and I wanted to relate this to polarography. So I did a bunch of different geometries of electrodes, and some of the results seem a little childish almost, you know, that if the diffusion was in the wrong direction, why then he got stirring, and so the current was much too high. Well, that shouldn't take all that much to appreciate that, but there had been, for instance, papers in the literature describing spherical diffusion, such as you have on a drop-in mercury electrode. And the point is that you could never hope to sustain this, you see, because the density gradients are bound to be wrong. They can't be right in all directions. And sure enough, you did this with a spherical electrode, and the thing would come down and then wobble along as you got some kind of a steady state. And so then later on I switched over to rotating electrodes so I could reproduce the stirring. I decided it was for the birds to try to have no stirring. It would take several minutes to get to a steady state after you change the potential. And nonetheless, I doggedly ran some curves to show that there's a parallelism if you can get to a steady state like this. But the real triumph came when I started rotating electrodes and reaching steady states very quickly and increasing the sensitivity by manyfold. So then we were able to do amperometric titrations and things like that at great sensitivity. So I did get something which I think was of some practical value as well out of it. But I always was thankful to Jim Lingame for having initiated in Kohlhoff's mind this study of electrochemistry, because he became so interested and he gradually gave up the precipitate work completely.
How would you describe Kohlhoff as a personality?
Well, of course he was from a foreign background in the first place. He came from Holland, and he went back to Holland all the time. So in the first place he had a very international scope, which is good for us, because he would have visitors from abroad that he would entertain, but his style was very idiosyncratic, if you please. In the first place, he would give you enormous numbers of problems to work on. He would spend the first 2 hours of his day looking at literature and jotting notes for all the students, you know. And then he would trot around along about 10:30 in the morning. He would just pass these out like a mailman giving out messages. And then he would come along, maybe the same day, maybe a few days later, and ask, did you do anything with that? Well, I learned that you didn't say no, you said not yet. And also I learned that he didn't really care if you did that. He was much more impressed if you had your own ideas. So usually I would say, no, I didn't do that yet, but see what I've got here. And oh, he immediately became interested. He put a little sour look on his face for just a fraction of a second, you know, what's this? And then you could see that interest sparkle in his eyes. And whatever it was, he became tremendously interested. So that was one characteristic. An enormously sharp memory for details. He could remember details of each student's thesis better than the student could remember them. And I learned later how he did that he did it by sticking to the essentials, not to the trivia. And there was always a purpose for doing an experiment, and whenever there was an unusual result, he struck on that, and he remembered that to the fine detail. So then we had this session of the system of what we call bull sessions. It wasn't a regularly scheduled set of research seminars, but whenever he got thinking about something, or he had one of these foreign visitors of some special interest, he would grab a group of us who were most nearly concerned with that and bring us into usually a classroom with a blackboard. And he'd tell one of us to get to the blackboard and explain something or other. And then the rest of us would listen, and we'd criticize, and the whole group would discuss it. It was a wonderful experience. I remember one time he brought in obviously a foreigner, and all I knew was that he wasn't English by native tongue, and he and Lingame, by that time, I was an advanced graduate student by then. They had already started on writing their polarography book. And he stuck me to the blackboard and he said, tell us about the double layer, because we want to talk about electrocapillary phenomena in the region of the electrocapillary maximum, and what absorption of ions would do to this and so on. So why don't you just talk about this a bit? Well, I started, and then what did he want? Well, he wanted me to trace the electrical potential profile as you traverse the double layer. And if you had an adsorbed layer of ions, you'd have counter ions and that sort of thing, and it went through a certain convolution. And what would that then do when you change the potential on the mercury? How would that change the shape of these things and so on? So I went through this. This visitor at sometimes would interrupt, and he would disagree, and we would discuss this. And I would say, no, that's wrong. Let me explain. And we went through that for some while. And then he trotted off with the visitor, and we went our own ways. And later on, I asked him, who was this fellow? Well, he said that was De Boer from Philips in Eindhoven. And I said, oh my God, why didn't you tell me this? I think that I had the nerve to argue with the fellow. He said, well, you must have done all right. Because he asked, would I be interested possibly in working for Philips after I finished? So, but it was a wonderful experience, and I guess we appreciated how really good he was. But I don't think really fully until later. He becomes the realization of how he could dredge these various things out. It was quite an experience. He really believed in research as a teaching method. A little impatient with courses. So he used to have a course which he called special topics, sort of an all-purpose course. And the rules of the graduate school were that we had to take a certain number of courses, at least in those days. And I had taken all of the undergraduate courses, you know, in analytical and in physical chemistry at Minnesota, and there wasn't much to take. So he said, oh, that's all right, we'll just sign you up for special topics. Well, he made those actually productive courses, though, because I remember that we had, for instance, a special topics in non-aqueous solvents. Now, he hadn't done any research on it yet, but that was his way of getting himself embroiled in a new subject. And the way he approached it was to assign us each a paper to read and to criticize and to present, and write a little report on. And then when he'd look at these reports, he would put caustic little comments. If he disagreed with something, he would put a comment like "brr," B-R-R-R, you know, with that exclamation point. He got your attention. But it was quite an experience. As it happened, I had association with Koldhoff for a lot longer than most, because we got it in the synthetic rubber program in 1942, late 42, and for 4 years I was involved with that, and I used to visit him then too, so we kept it going. And besides, I had my family, several members of the family living in Minneapolis at the time, so I always welcomed a chance, excuse to go there. And so I was sort of the contact person between the Illinois polymer group and the Minnesota one. And so I enjoyed those visits. And then even after that, I visited him every year. I make a point of doing this. I spend about a half a day or better part of a morning with him. As he's gotten older and so on, our discussion gets less technical and more reminiscences type, but we have a wonderful time.
How did you learn of the spinning electrode?
Well, you mean the rotating disc?
I mean,
yeah, well, that was invented by the Russians, actually, in the late 1940s. I had left Minnesota in 1940, and prior to that time, we used primitive forms that weren't really very good hydrodynamically. They were just rotating wires and so on, so the hydrodynamics were not good. But the Russian workers did a complete theoretical analysis of this and showed its characteristics. But by then I was no longer interested in solid electrodes, because I had decided that the worst thing a young instructor can do was to keep on doing what he did for his thesis, you see. So I stayed away from that, except for certain applications that had to happen. Like in the rubber program, we had to titrate mercaptans, and that was the best way to do it. So I did it. But as far as research is concerned, I turned to the dropping mercury electrode. I don't suppose people really believe that was much of a departure from the other one, but to my mind it was. And so for that reason, I just ignored this. And then years later, after people got involved with using all kinds of different electrodes, you see, because electronic techniques had advanced a whole lot in the decade, say, following 1940. So by 1950, you could make measurements you wouldn't dream of making before, like pulse measurements and AC impedance measurements and all that. And so at the same time then, other people had shown some of the real advantages of rotating disk geometry for such work, for kinetics and analysis as well. And then derivatives of that, like the ring disk electrode and so on, which are extremely powerful electrochemical tools. But things really changed in the decade of the 1950s. See, so much advances in the way of electronic techniques. I can remember I didn't have an oscilloscope in my lab until 1955, and that still wasn't a good, stable, DC coupled scope. And but a key year for me was 1953. I went over to England on a sabbatic and worked with John Randalls and learned about impedance techniques, which then brings you into the realm of electrokinetics. And so from that time on, I took a different approach to electrochemistry, much more mechanistic type approach. I was never one to try to work on new techniques, especially, but I was much more interested in using the techniques as they came along to solve problems. So we spent a lot of time on molten salt electrochemistry, because the techniques were there, but they hadn't been applied in such solvents, and it was a much more difficult thing to do. So it kept me going for a part of my research effort for something like 30 years before I finally gave it up.
How did you come to catalysis?
Well, that's a little of a story too, because in the process of trying to make this lead determination, we found that there was a carryover of lead from one solution to another, and they seemed to persist on the electrodes. And we were able to trace this down to an adsorption, an irreversible, strong chemisorption of lead on tin oxide. Well, that struck me as being interesting. So when I moved to Florida in '74, and we got, Gar wasn't here yet. He came, I think, about 4 or 5 years later. But I decided that we might be able to make some use of this by actually putting on metals like platinum onto the surface. And what use I didn't know, but we might be able to use it for something. So we undertook a study of it, and sure enough, we could get platinum on it. And then when Gar came, and we could examine these by ESCA and all these fancy methods, we became close friends and really enjoyed our collaboration on this. And we still are, as you know, collaborating on. I've always thought it's great if somebody can encompass all these techniques, but I couldn't imagine taking the time and struggle and so on, learning all about the surface spectroscopy and get the equipment and all that. But it was wonderful to have someone who was interested in my kind of chemistry. And Gar, in his turn, he had been brought up on single crystals of pure metals. And he was in chemical engineering, after all, and he was searching for problems that were closer to real world. And so to take a polycrystalline material was already quite a departure from that. And so he enjoyed that aspect, and we combined our talents pretty well, I think. I think it's time for lunch, you know.
Yes. Well, I certainly think how they got into science, catalysis.
The way I got into catalysis is through a series of